best software library for modeling and simulation of solar desalination systems. www.reslibrary.com.
Hi everybody, Professor Mohammed Shar with you. Today we are going to talk about solar photovoltaics combined with vertical wind turbine for reverse osmosis desalination plant. What is the main concept? How can we run our model? Let's see. As demonstrated previously, the main concept of solar photovoltaic combined with wind energy, it's used to power reverse osmosis desalination plants, which can provide fresh water for remote communities that don't have sufficient natural resources. Remote communities are often located in areas with access to seawater or brackish water, groundwater, or high saline water, high percentages of saline water. For such communities, small scale of reverse osmosis or even larger scale desalination can provide fresh water. Solar photovoltaic can be easily used to power on reverse osmosis high pressure pump. Also, we can use energy recovery. If we are going to talk about large scale reverse osmosis plants, we can use energy recovery devices such as fuel cells, wind turbine, vertical wind turbine, or even horizontal wind turbine, batteries banks, control room, and so on. So in our example today we are going to discover the large capacities, how it can be operated. For example, reverse osmosis, briefly, it's such kind of water purification technology which uses semi-permeable membranes to remove ions, molecules, and larger particles from drinking water. It is quite applicable for drinking water purification, military uses, food industry, hydrogen production, tourist spots and tourist areas, and something like this. For reverse osmosis, we can utilize three main configurations. We have basic module, built-to-wheel turbine as an energy recovery device, and pressure exchanger as an energy recovery device. Of course, pressure exchanger is the most efficient one among all of these configurations. Its efficiency, we can talk about 98% or something like this, comparing against 80% for built-to-wheel turbine energy recovery device. For basic module, it's basic. We have one input stream through the high pressure pump. This is the inlet feed stream going through the membranes, and we have two output: ejected stream with high concentration of salinity, high pressure, and we have permeate water or low concentration with we can consider this the fresh water. We can utilize or use built-to-wheel turbine with the rejected brine that rejected from, because it's a high pressurized stream going outlet from driven outlet from the membranes, so we can use it as a rotational fluid or power fluid or hydro fluid for built-to-wheel turbine, in order to reduce the power consumption or the power load on the high pressure pump, because this load on high pressure pump is a load considered as a load on the photovoltaics or vertical wind turbine, or what is I mean it's a huge load on the source, especially if we are going to talk about massive production. The same technique fits for pressure exchanger device. We can exchange the pressure from the outlet brine with the splitted feed from the inlet in order to transfer the high pressure from the brine to the feed. Splitting the feed at the inlet will also reduce the pressure on the pump, and so the load on the load or a specific power consumption at the same time. Okay, for our model, we are going to utilize vertical wind turbine, photovoltaic system, reverse osmosis with different configurations, 3 configurations, and the control room for cost estimation and load variation between vertical turbine and photovoltaic system. You can utilize which, depending on full load on photovoltaics or full load on vertical wind turbine. We can go to our destination folder. Okay, double click on this is 2 models. We have to consider this just the second one. Okay. Okay, the model should appear like this, and as you can see here, this is the main panel. There's some information about it. Okay, and this is our control panel. First of all, it's a design model, so we have to deal with firstly the reverse osmosis. We can assign our input data. We can assign the following. First of all, we have to choose between 3 configuration. I'm going for the simple one as a basic module, and we have to assign operating conditions such as ambient temperature or keep seawater temperature, and this is salinity ratio. It's I'm going for 45. This is almost Red Sea salinity. 45,000 ppm. Productivity, plant productivity, let's go for 3,500 meter cube per day. Okay, and then we are going to choose the membrane type. I'm going for seawater, high recovery ratio 380, and this is area, module area. Okay, you can assign a number of pressure vessels and number of element per vessels. Number of elements, I think for 3000 we are talking about 38 elements per vessels. There's some performance, high pressure pump efficiency, fouling factor, and recovery ratio. Because it's a design module, I'm going for 30% recovery ratios. Okay, and the rest is for some operating condition for built-to-wind turbine. This is pressure exchanger. So we are going to talk about the basic module. Okay. Okay, the productivity, assigning the productivity will calculate or should be responsible for the load on the photovoltaic system or vertical wind turbine. Okay, let's go for control room unit. We can here control the load variation between photovoltaic and vertical wind turbine unit. For suppose I'm going for 0 means full load on photovoltaic system. Okay, and 1 means it's from 0 to 1 is full load on vertical wind turbine. I'm going for, suppose I'm going for 50%. Let's go for 50%. Okay, Okay, let's go for vertical wind turbine. You can here assign, sure, but we have here the cost analysis, this plant lifetime, this capital cost, and interest rate, and I will keep these parameters. Okay, for vertical wind turbine, we can try some operating conditions and the design. Which module you are going to use? We have to deal with a 0.2 kilowatt module up to 50 kilowatt module. I'm going to use 50 kilowatt because it's massive energy, massive power load, and so on. For photovoltaic system, we can utilize two types: solar radiation, instant solar radiation, or total hourly or total daily solar radiation, kilowatt hour per meter square. I'm going to utilize instant solar radiation. Let's go for this. And now our model is ready. But if you go inside the photovoltaic, you can calculate mass flow rate, started wind speed, rated wind speed, rotor diameter, swept area, fan length, rotor RPM, torque, power coefficient, number of vertical wind turbines, and the voltage and cost. Okay, for photovoltaic system we have two modules. What instant, and this one, as you can see here, we can calculate number of modules, cell area, module area, total system area, and so on. And the same for both modules. Okay, let's hit run and see. We have to watch. This is basic module, Photovoltaic turbine module. This is basic one, Photovoltaic turbine, and this is pressure exchanger. Let's go for basic. Okay, we have to watch this to adjust the pressure, high pressure, the pressure, not the high pressure pump, regarding to the number of element per pressure vessels. Let's hit run and see. What is this one? This pressure. Okay, the pressure is almost 71 bars. I think this is a little bit high, so we have to increase our number of elements. Let's turn back and increasing the number of elements up to 40 elements. I'm seeking 68, 65 bars and so on. Let's hit run again. Yes, 69. It's quite good. Let's increase it a little bit. Double clicking. Let's go. We are going to assign 42 pressure vessels, and let's hit run. It's okay. 68 bars. This is a specific power consumption. This total area. Okay, and this is the power, 1 megawatt, almost 1 megawatt. You can discover the mass flow rate of the feed, inlet mass, because it's a design model, brine loss, salinity of the brine, salinity of the distillate, the product, and this is average brine salinity, specific entropy production, irreversibility rate, feed exergy, brine exergy, product exergy, and salt rejection percentages. Okay, for this we have to watch our photovoltaic system. Let's see. Sure, we divided our load between vertical wind turbine and photovoltaic. Let's go first for vertical wind turbine. Oh, okay, this is mass flow rate. This is starting wind speed. It's 2.9. rated wind speed is almost at 12 meter per second. This is rotor diameter is 9.5 diameter. Remember, it's a vertical wind turbine unit. This is rotor swept area, fin length, RPM, and torque. This is wind power. This is power coefficient. It's 9%. This is a number of vertical wind turbine. We need 10 vertical wind turbine, almost 10. And this is number of blades and so on. This is the total cost of the vertical wind turbine. Okay, this is the load on because it's 50-50. I mean, this is power load on vertical wind turbine. It's 500 kilowatt, and I think this is the same for over photovoltaic system. It's a power load on for photovoltaic. It's 527. Okay, let's go for photovoltaic system. This is instant one. Yes. You can discover open circuit voltage, short circuit voltage, maximum voltage, maximum current, module efficiency, dimension, cell efficiency, number of cells per module, and this is full over for price, US dollar per watt per module. Okay, this is total number of modules you are going to assign. This is cell area per module. Module area. This is module area, and this is the total system area. We have to deal with 3,400 meters square for 5 kilowatts. Sure, we can control this one because we can go to the photovoltaic system and we can reconfigure some parameters. This operating hours. This is number of cloudy days, and solar flux is 1,000 watt per meter square. I'm going to consider this. Okay. For design, you can choose your module type. I'm going for 220 module type with battery depth of charge, efficiency of the battery, and the cost of the batteries. Okay. Let's return back again and go to the photovoltaic system and hit run. Okay, the module type is changed. Module area, cell area, sure. Battery hour, ampere hour, and number of batteries, and this is the total cost. This is the total cost of photovoltaic. In order to sustain for 500 kilowatt load as a demanded load on the reverse osmosis high pressure pump. You can discover membrane costs, annual replacement costs, annual fixed charges, annual chemical costs for reverse osmosis, annual labor costs, annual vertical wind turbine, and you can. This is unit product cost. We are going to sell our product with this price, 0.6 US dollar per meter cube of fresh water production. Okay, you can go for actually you can go for dynamic model by set your simulation time up to infinity, and you can hit run, and you can change the productivity, the load, the solar radiation. As you can see here, I'm going to checking this one. Okay, let's say checking the load between. I'm going to fully load on vertical wind turbine. Okay, and let's return back again, and you will realize this change. Okay, I'm going for 40%. Okay, let's go for solar radiation. I'm going here for solar radiation. Let's change our solar radiation down to 500 watt per meter square, and we can see the variation on the areas and the module area, battery storage, battery capacity. Okay, and let's change the productivity. I'm going to change the productivity. I'm going for 5,000. 5,000 will increase the load. And sure, if you increase this, you have to increase the membranes. I'm going for 10,000 meter cube per day. Let's watch here. Yes, the changing. There is some changing in pressure and the power, specific power consumption. I'm going to let's go for increasing the membranes. Yes, increasing membranes up to 120 elements. Let's go for, yes, decreasing the pressure, adjusting the pressure. As this is 3 megawatts. Okay, let's hit stop. If you go, let's go to here. You can here collect your data, output data. You can collect it from here. Okay, let's go for. Okay, let's go and watch our variations. These are parameters here. Let's go for power load on. This is on photovoltaics, and this is some change of solar radiation and decreasing and increasing of the load variation. And this is load on photovoltaics. Okay. For load on photovoltaic, you can the specific power consumption. This is irreversibility rate. This is exergetic feed, exergy of the brine, and so on. And this one is power on the high pressure pump. This is mass flow rate of the feed, mass flow rate of the brine, and this is exergetic salinity of the brine and average salinity. Okay, let's go for number of vertical wind turbines. Yes, number of vertical wind turbines, mass flow rate, air. This is yes, almost. Yes, we can go for area. This is cell area of the photovoltaics. This is module area, and this is total system area. As you can see here, it's changing according to the variation of many parameters that you can address. It's up to you as a user to make this parameter constant and to control the other one and so on. Let's send this to the figure. You can send it to the figure. It's easy with Simulink. Okay, as you can see here, there's our figures. You can control it, you can draw some parameters and so on. As you can see here, this is your simulation time, and this is your figures and variation. You can address control and so on. Okay. For this, you can, as a result, the load variation along simulation time is presented in the following. This is another example, is for a tiny power load. Decreasing the load on the PV will lead to operate vertical wind turbine besides the batteries. Batteries would be operated till the next daylight. Any decrease in the PV operation will be followed by an increase in battery ampere hour and the capacity along the day. As you can see here, decreasing the load on the photovoltaic would be followed by the operation of the batteries. Besides the operational time of the vertical turbine in order to recharging the batteries or something like this. At the same time, daylight decreasing the load on the photovoltaic on the vertical wind turbine, followed by the increasing the normal increasing of the load on photovoltaics, will followed by some kind of decreasing in battery storage, fully depending on photovoltaic and so on. Finally, don't forget to download our waste gases cycle for thermal desalination processes. It's for we are going to utilize waste gases from oil refineries. We are not going to burn it in the air anymore. We are going to withdraw these harmful gases in order to utilize it with a steam generator. And this steam generator is going to power on a multi-stage flash with brine heater, and the condensed steam is going to be reflashed again to operate MED. It's a hybrid cycle, and the accumulated steam will be repumped again to the same generator. We have another cycle with the same idea, but for gas turbine cycle. We can use this, handle these harmful gases to be burned in combustion chamber with high pressure gas turbine and low pressure gas turbine, and the exhaust gases is responsible for how to power on thermally the brine heater for multi-stage flash desalination. Thank you for watching. We are looking forward to hear from you. Please give us like, share, subscribe. Thank you again.